My name is Christian Mendl. I talk about a real-time evolution method for neural network quantum states, and this is joint work with Irene Lopez, who went through also hard work of performing all the calculations I will show in this presentation. Okay, so the motivation is, okay, we want to simulate the real-time evolution of a quantum state psi. And I mean, of course, this is especially when doing this like on a classical computer, this is computationally very challenging. And one also knows that tensor network methods are kind of limited by entanglement growth. So one expects that one can only reach relatively short timescales with this method. And this is, of course, well understood. And as the title of this conference kind of implies, what we explored here is a neural network quantum state to parameterize the wave function psi here. And specifically in this talk, we will consider a discrete spin variable as input. So this sigma is just a vector of, so to say, binary strings. And then we feed it through this classical network, and it outputs psi at this spin configuration. And we will also, by the way, use explore like a convolutional layer. And I should also mention that these internal weights and bias functions or bias values are complex valued. Okay, and the approach we explore here is somehow similar what Brian Clark also presented in his talk. So in some sense, we want to learn the wave function at the next time step. So here we collect the parameters of our ansatz or of this neural network in this variable theta, and then we have a new set of variables for each time step. And what we want to minimize is basically this expression. So the wave function at the next time step should represent the flow of an ODE method. So this is this phi of delta t, which we apply to the wave function at the current time step. So ideally, we just follow the flow of an ODE method. And specifically here, we consider the implicit midpoint method, which has two favorable properties. First of all, it's symplectic, so this is well adopted to Hamiltonian systems. And from a practical side, there are no intermediate quantities appearing here. So this is, just makes the computations simpler in practice. So when we apply this to the Schrödinger equation, we arrive at this expression here. And note that the method is implicit, so the sub psi at the next time point appears, so to say, also on the right side of this equation and on the left. And so ideally, we want to have an equal sign here. And now, I mean, this leads directly to a cost function. So one thought which goes into the definition of the cost function is that we don't want to actually invert this Hamiltonian matrix here. So we just resort or reorder this expression as shown here. And then since we cannot, I mean, in practice, for larger systems, one cannot evaluate this at all possible spin configurations. So we just sample over input spin configurations and define the cost function accordingly. And now a short note on stochastic reconfiguration, which would be kind of the canonical choice here. But so to say, our method is in some sense an alternative, which we hope would avoid some of the problems associated with stochastic reconfiguration. Namely, there you would have to solve a linear system, but this covariance matrix S is typically singular or almost singular. So this can cause some issues or problems, especially for larger systems. And in our method, we would, so to say, bypass this issue. All right, and then another aspect we put some thought into namely the backpropagation with complex parameters. So first of all, we can like concisely represent the cost function in this least squares form, where this A matrix now collects the rows of identity plus I delta t half of the Hamiltonian corresponding to these spin configurations which we sample, so to say, and the entries of the B vector are defined like that. And now, yeah, to compute gradients, we make use of the so-called Wertinger formalism, which puts it, so to say, on a yeah, just a mathematical framework behind that. And I mean, the thought behind that is that in general, or for our case, so to say, the cost function which we want to minimize is not a holomorphic, or I mean a complex analytic function, because it's, I mean, of course it's real valued, right? And in this case, yeah, it cannot be holomorphic except for a trivial case of a constant function. But on the other hand, this Wertinger formalism allows us to compute gradients, and we apply this. When we apply this to the cost function above, we arrive at this expression here. And another important aspect here is that when we since we already know that this cost function is real valued, we can exploit this for the Wertinger chain rule. So what this means in practice is that for each parameter of our network, we also just need to store a single complex number for the gradient, okay, instead of like a 2x2 real matrix, so to say. So instead of 4 parameters. And another aspect here is that we on purpose have chosen the operations inside the neural network to be holomorphic. So the sub psi itself, so to say, is a holomorphic function of the network parameters, and this has the advantage that we can use conventional complex derivatives inside the wave function, so to say. All right, so let's show some numerical examples. So we consider here the time evolution governed by the Ising model. And first of all, the top left plot shows the error, so to say, for a 1D lattice with 20 sites. And here for the, we use a restricted Boltzmann machine ansatz for the wave function. So the y function as a y-axis shows the overlap error on a logarithmic scale. And so first of all, the dashed curve is error of the exact midpoint method. So of course this also has some error associated with it. But we cannot, I mean, we cannot hope to be better than that, right? But according to the plot, so to say, the main contribution from the error is actually coming from the from our parametrization of the neural network. So the orange line is our method, and for comparison, we are also showing here the stochastic reconfiguration as a dotted green line, and at least for this model system, they fare comparably very similar, right? And then on the right side, this is the error for a small 3x3 lattice, and here's the wave function itself consists of a convolutional layer and a dense layer, right? And again, the dashed line is the error of the exact midpoint method, and the orange curve would be then the error of our method. And what this our ansatz also allows us, so to say, to plot the filter weights of our ansatz. So here we use as filters in the convolutional layer 5 2x2 matrices, and this plot shows the amplitudes here and the complex phases of these filters for different time steps, so time 0 up to time 1 here. Okay, and I also want to just say a few words about the implementation details. So this was first of all, yeah, kind of, so the core of it is written in C code, where we have also implemented kind of neural networks, at least these aspects what we need here from scratch. So including, for example, convolutional layers, this so-called int-to-call operation to rewrite this as a matrix-matrix product. Yeah, we construct selected rows of this Ising-Hamiltonian as sparse matrix. So remember, the rows are determined by the sample spin configurations. Then we use OpenMP for parallel gradient computation. We store the network in a HDF5 file, and we can use a Python interface to make this conveniently accessible. Okay, here's just a short code snippet showing the like part of the C code for the conv to the backward pass. All right, so this brings me already to the conclusion. So the main idea here is to use a direct ODE approximation as a kind of alternative to stochastic reconfiguration, and we expect that this could be advantageous especially for deeper networks. So when you have many more parameters, yes, due to the issues with the singularity of the S matrix in stochastic reconfiguration, there are many ways for improvements. I mean, of course, this is the results are shown are more like, yeah, toy model systems, so to say. So this is not really impressive, but we hope that this can be further extended and improved. And one, so to say, feature or possibility would be to change the network architecture on the fly. And then, yeah, by the way, there's also kind of parallel work by Marco Schmidt and Markus Heil, who use, who actually puts a paper at the same day on arXiv, and there will be also a talk about this work, I think, later in this conference. And they used a very similar ansatz, but eventually reached just much larger systems. And as an outlook, we also want to explore so-called neural ordinary differential equations, which kind of are hopefully adapted to time-dependent problems. All right, that's it for the presentation. Yeah, many thanks for the attention, and then I will take some questions now.